the video I posted on D12.
If we have time,
and if we have time, we can go through and do some other questions as well.
So graphing
is kind of a big deal. It's one of the problem areas that students sometimes have with calculus.
So the idea is when you're doing a trig function, you've kind of got these pieces right here. I'm going to use the letter A to represent that negative 1/2. I'm going to use the letter B to represent that 2. I'm going to use C to represent that. Okay. So this thing is already in a factored form. So there's some things that you have to know. We have a formula for the period of the trig
functions. If you're doing the sine, the cosine,
the secant, or the cosecant, the formula
is the period is equal to 2 pi
over the
absolute value of b.
Okay. But
if you have a tangent and a cotangent,
that period
is going to be pi over b. So that's a real important aspect of your graphing, is know what the period means and how to find that. Okay.
So if we go
through and do this, since this is a secant,
the period
is going to be given by the formula
2 pi over
absolute value of b. And the absolute value, all that means is your period is a positive number. It's always a positive number because it's a measurement.
So with this one,
you're just going to take
2 pi over 2. That's your b value right there. And then that will
give you pi.
And what that's
going to mean
is
every time pi radians goes by, it's going to go through one cycle of this secant.
And every trig
function has 5 key points.
As a beginning point, and then 4 more points to complete
that cycle.
Okay. Next thing that you do,
and this is always the same. When you do the increment,
this tells you how to break up the x-axis.
You always just take the period,
divide by 4.
Okay,
so when we do this,
we're just going to do
the period
over 4.
So the period's
pi.
Divide that by 4.
Then we get pi over 4.
Okay, so that's what
that is.
And it's super important when you do this. If you're gonna,
this is what really simplifies graphing trig functions, is to get that increment.
And then what you can
do is you just count these things out. So
you count
by the numerator pi over 4, 2 pi over 4,
3 pi
over 4,
and 4 pi over 4,
and so forth. Doing that, and then you reduce the fractions. So
what I'm going to do on this is just
break it up and label this. You need to label each one of these things.
That's pi over
2 because I'm reducing the fraction.
This is 3 pi over 4,
and then that's pi again. I'm reducing the fraction.
The directions
to my problem say graph at least one period
beginning with the
phase shift. Anytime your function has a phase shift, the best place to start is with that phase shift. We'll talk about that in just a minute.
Okay, so I'm going to go over here and I'm going to do
the same things.
Get that set up.
So the increment, what's so important about that
is it tells you this is where all of the special points on this graph
are going to look.
Everything
here can be values that can come out of the unit circle if you do this then.
Okay.
Do we have any questions so far about how I found the period
or the
increment? Any problem with that so far?
Okay. All right. So
next thing we're going to do is look at the phase shift. So the phase shift
is this
number right here.
That's the C number. And if it's plus,
that means you're going to go to the left.
And if it's minus, that means you're going to go to the right.
College algebra recently,
you learned how to
do those left-right transformations. That's what a phase shift is.
So our phase shift,
we will just say
3 pi over 4, and then to the left.
You can also put negative 3 pi over 4
because it's going to the
left. But I don't care which way because it doesn't matter. What matters is that you know what the phase shift is, and if you're going left or right.
Okay, so that'll kind of get us
going on that. Now, if you do a secant,
the thing that you want to do when you graph a secant
is you want to really focus on this. You want to graph
the cosine. Okay, so what we're going
to do is we're going to graph out
y equals negative one half
times the cosine
of 2 times x plus 3 pi over 4. Okay, so we're going to focus totally on that. Now let me show you kind of how you can do this. You can learn to do this all in one step. Okay, you really can. If you get everything memorized on the cosine and sine and how the graph goes, then it's pretty easy to do. I'm going to go ahead and just do my y-axis probably kind of like this. I'm just going to go up to 1, down to negative 1, and then I'm going to put a half in there. And a negative 1 half. The reason I know to do that is because that amplitude's a half. If the amplitude of your cosine's a half, that means the max will be a half and the minimum will be negative 1 half. Okay? This doesn't have a vertical translation to it. So again, what we do is the cosine always starts at a high point. Okay, so what I'm going to do is we start at the phase shift, which is negative 3 pi over 4 to the left. And what I'm going to do is just lightly put a dot there. And then I'm going to cycle through the key points on a cosine. You have the max, what we call a midpoint, a minimum, another midpoint, and then we get back to a max like that. That's 1, 2, 3, 4, 5 key points. That's what's going on in the problem. Now, what I'm going to do is the negative 1 half is going to multiply those y values. So if you look at these y values, we have a y value of 1. If we multiply that by negative a half, then that's going to move that point to negative 1 half. Okay, then I'm going to scratch that out. Okay, so what I'm doing is just doing the amplitude after I get the basic cosine wave. Okay, if I take this y value of 0, if I take negative half times 0, that's still 0, so that problem is set where it needs to be. The other thing is this point is negative 1. So if I do negative 1 times negative 1 half times negative 1, I'm going to get positive a half. So this point moves to here. And then the nice thing about a cosine and sine is once you see the pattern, then you can just fill it in. So from here it's going to go to the midpoint. It's going to go to the minimum, to the midpoint, to the max, and back to the midpoint. Okay, so you can just fill all those things in. And then I'm going to use a dashed line to represent that is the graph of the cosine. Okay, good place to pause and see if you guys know what I'm doing here. Or anything that I need to clarify. Anything you got a question on? Okay, are we okay? Give me a thumbs up. Or something, so I can see if you're there, and if you're alive, and you know what's going on. Okay, Ricardo is good. The rest of you have a little thumbs up. Okay, Nathaniel, there we go. Awesome. Felipe, you there? Okay, all right. Okay, very good. Now what we do is we do this. Okay, every place that you have a midpoint, that's going to give you what you call a vertical asymptote. This is how the secant graph goes. So what I'm going to do is in all of these midpoints, I'm going to put a vertical asymptote. Okay, that's the way the graph works on a secant and a cosecant. So you want to make sure that you represent those vertical asymptotes like this. All right. And then all we got to do to get our graph is we just sketch the graph. The nice thing about using this technique is now all we got to do is just sketch this. Okay, so the final graph on a secant, what it does is it looks like this. On the maximum, it kind of is a U shape. You want to draw it so that it's approaching the vertical asymptotes but not touching. Okay, then that will go like that. And then the bottom, the minimums go down like that. Okay, and that's it. So you got a nice accurate graph. The key to doing a secant is to graph the cosine. That's what your final graph looks like. Okay. All right. So the asymptotes with the midpoints, then you sketch those U shapes. Okay. The other thing is the equations of the vertical asymptotes. Now what I'm going to do is I'm going to write down every one of these vertical asymptotes is. One of them is at 0. The other one is at pi over 2. The next one's
at pi.
And over here,
you've got
negative pi over 2. You got negative pi. So you have to write a formula
when you do this.
If you go through and count
these things out,
that kind of works like
this. You really have 0 pi over 2, 1 pi over 2,
and 2 pi
over 2.
So you would know the next
thing would be 3 pi over 2.
So what's happening
is you always have a pi over 2 in your formula.
What's changing is these numbers in front.
So you can write the answer to the equations of the vertical asymptote as x equals,
and then you just say
k pi over 2,
and then you have to state
that k is an integer.
So you can
figure out that formula by observing the pattern. That's one way to do that.
Okay, and if you don't like that,
a lot of times students have a very hard time seeing the pattern.
There is a formula,
and it'll go like this. You just say x equals
like the first
vertical asymptote that you find. I don't care which vertical asymptote you pick.
Then you would say
plus 2 pi k,
plus the
period. Times k, and then k would be an integer.
So you could also
write your answer like this. You could say x equals,
and just pick an asymptote.
I'm going to pick 0. That's a real simple one.
The period
is pi.
If you go back to
pi is the period.
Go back to
question A.
So then what you would say
is 0 plus pi k,
or just x
equals pi k.
And what it'll be
is half of that period.
So the formula you can use if you prefer to
is this.
So you just pick a vertical
asymptote.
Then you do half
of the period times k.
That's the way it always works
on a cosecant and secant.
So we just say
1/2 pi k. K is an integer.
A lot of students tell me a lot of times that the hardest part of these kind of problems is getting the equation of the vertical asymptote. That's from experience what students seem to have the most trouble with. Okay, is there any question about what I did on that with asymptotes or completing the graph after I did the cosine? Okay, everybody okay? Okay, thumbs up if yes. Ask a question if no. Okay. All right. Now what we would have is with this next thing here, the domain. You just have to write. It's intervals. So you would find that you have a graph between 0 and pi over 2, and then you have a graph between pi over 2. And pi. And all you got to do is just kind of list this out, and you can put the 3 dots to show the pattern. And if you go backwards like this, it would be negative pi over 2 to 0, and then just have the 3 dots like that. So that's good enough. It's just in between every asymptote is where you have a graph undefined at the asymptotes. Okay. All right. So if you're ready, then we'll go ahead and we'll move on to the next question 15, which is a cosecant. On your review, I tried to give you one of each graph. And this is actually very, very similar to what I just did. Okay. So if you have a cosecant, then what you want to do is ultimately you want to graph the sine. So ultimately in this problem, we're going to graph the sine in a dashed line, identify the midpoints to get your asymptotes, and then sketch the U-shapes. So secant and cosecant work kind of the same way. Okay, first thing we got to do is we got to factor. And it's real important if it's not in a factored form, you always factor out whatever's in front of x. Okay, so this is going to go like this. If I take that out, I've got draw a bracket, and I'm going to take the pi out. And we need to figure out what goes inside. Okay, so this is sometimes hard for students to do in their head. What you can do is you can take the pi x minus pi over 2, and when you do that,
you're taking out a common factor of pi.
So what you're really doing is
dividing
both of these things by pi. Okay, so that'll give
x.
This part right here is going to be pi over 2 divided by pi. So that will be
pi over 2
times 1 over
pi.
That gives you 1/2. So when you factor that,
you have x minus 1/2. You don't have to go through all this stuff.
You can process
that in your head.
So your factored form is y equals cosecant
of pi times x minus 1/2
minus 1.
Okay,
and again, think something that's super important when you're doing this. If you factor, make sure that you check it. You have pi times x,
that gives you pi x.
Pi times a
half gives pi over 2.
Distribute to make sure it's right. Because if you mess up in the factored form, you're going to mess up on the whole problem.
That's how important it is.
Okay, so it's going to work the same way now. This is going to be B. A
is actually the number in front, which the number in front is 1.
So you have an amplitude
of 1.
C is going to give you your phase shift.
At this time, D is going to just make things go up and down. Okay.
All right, so it goes like this.
The formula for the period
is the same as it was on the last problem.
2 pi over
absolute
value of B.
So what I'm doing
is I'm doing 2 pi
divided by
pi.
Okay, the B value is
pi, the pi's cross out.
So our period
is equal to 2.
So always just
take 2 pi divided by
the B value,
the coefficient of x,
to get that period. Okay?
It's okay if it's just a number. What that's going to mean is every time 2 units go by
on the x-axis,
you'll have a U-shape going up and you'll have a U-shape going down.
A period of a
cosecant looks like this. You have a U up and then you have a U down.
Over and over again
like that.
Okay? And then the next thing
is the increment. What you do is you take the period divided by 4.
So the period
is 2.
Divide that by 4.
Reduce the fraction, get 1/2.
And going through the increment to me is the most important part of this problem. Because this is going to tell you where all your key points are. So we just count by a half.
We go a half.
2 halves,
3 halves,
4 halves,
and
reduce
fractions as you go through that.
So that's a half. 1, 3 halves, and then 2. So you made it all the way to 2 units. When you count to 5, 1, 2, 3, 4, 5, you should be at the end of the period. Okay, that's how that works. And then over here, we have negative a half, -1, -3 halves, and then -2 like that. Okay, so we're all set up with everything that we need to get that. We
did the factored form, we got the period and the increment,
we've got our
x-axis set up.
Okay, does anybody have a question about what I've done on that
so far?
Okay, be careful with that factoring
when you do that. That's really important.
So now we're going
to just go ahead and identify everything. Your phase shift
is this number right
here.
This is just
moving the graph
left and right. Since that's a minus,
your phase shift is going to be to the right
1/2. And anytime your function has a phase shift, that should be the place where you start drawing
right at that phase shift.
And then work from that phase shift. Okay, the vertical translation
is this number.
And since it's
minus, the y values are getting smaller, it means everything is moving down.
So that would be
down 1.
So that's what you would have. So what
we'll do is since this is a cosecant,
we're going to focus
on
the
sine wave.
And if we can get an accurate
sine graph,
then it'll be
easy to finish up the problem.
Okay. So here's what I'm going to do
on this.
You have an amplitude of 1. Your amplitude is 1.
That's the number in front of the trig function.
That's going to tell you that you
have a max
at 1 and a
minimum at -1.
And then you have this vertical translation of -1. So you got to move
everything down.
So the most logical way
to scale
this y-axis
is to go down to -2 because you're going to be moving this thing down 1 anyway.
Okay, now you
can do this in multiple steps. A student can learn how to do this all in one step at their head.
Okay, when we do the phase shift,
that just means that's where we're going to start.
And what you have to know about a sine wave is a sine wave.
It starts at the x-axis.
Okay, so I'm just
going to write these points. We're going to adjust these points.
So we're starting at the phase shift.
Then we go up to the max.
Then we go back to
the x-axis.
Then we go like that. Okay, that's right there.
That's right there is
you could also kind of go backwards. That gives you 1, 2, 3, 4, 5 key points. All right. Now what we have to do is all of those things have to be moved down 1. So I'm just going to kind of do this in my head. This point right here is going to go there. The 1/2. That point, it's an x-intercept, goes down there. This point goes here, and so forth. So we're just moving all of those points down 1 unit. Okay, and then what you can see is this would be one period of this sine going from 0 to 2. That gives you your 5 key points. Then you can work backwards. It's got the pattern. So over here you would have this midpoint. You'd have an x-intercept, another midpoint, then a minimum like that. So the big work of this problem is graphing the sine wave. Once you do that, you're in business. Okay, good place to pause and see if anybody's got any questions on this. Does anybody have anything that they don't understand as to what I'm doing? Okay, all right. So the asymptotes, where the asymptotes occur, is at these midpoints. The midpoints. Yeah, Felipe, I do that. There's a formula for the period. Okay, and I'll do that in just a minute. Okay, so these are the places where the vertical asymptotes are. The midpoints are those points that I highlighted in yellow. Okay, so you just sketch in your vertical asymptotes. And then once you do that, then you're ready to sketch the final graph. Okay. All right. So now we should be able to finish it up pretty easily. So what we do is sketch in the shape. That's the U shape. Just make sure it gets close to the vertical asymptotes. Same thing here. That gets close to the vertical asymptote. The U shape goes down. If there's a minimum, the U shape goes up. If there's a maximum, so that would be your graph. Now what I said in my directions is I said just graph one period. You can graph more than one period, but you just got to make sure that you have one period in there with 5 key points. Okay, so that's it. That would be the graph of that function. Okay, and I do want to show you all one other thing on this problem too. But Felipe, to get your question. Okay, basically the period has a formula to it. Okay, the formula is 2 pi over absolute value of b if you are doing the sine, the cosine, the tangent, or the cotangent. Okay, that's what that is. The period is pi over b. If you're not the tangent, I put the wrong thing there. I'm sorry. Sine, cosecant, secant. These four trig functions have a period that's 2 pi over b. The tangent and the cotangent are different. It's pi over b. And again, if you look at what I did here, b is this value that's in front of x. In the beginning problem right there. You take 2 pi divided by that coefficient of x. That's how you get the period. Okay, you got that? Okay, you got that, Felipe? That's how you find it. There's a formula to it. Okay. Okay, very good.
Okay, very good.
Okay, so that would be that problem.
And that's what we need to do on that. Let's see, is there another part on this?
Okay, guess that's
pretty much it then.
Okay, so that's
kind of the graphs. And again, if we have time,
we can go back
to doing the cotangent and tangent graphs that I did on Monday night. So
that kind of gets
me away from the graphing. And graphing is a big area of trig.
It's one of the problem.
It's one of the problem areas. So try to do the strategy that I'm trying to show you for graphing, because I'm showing you
kind of a simplified
way of doing this.
Yeah, Ricardo.
You have a question?
Yeah. So real quick, are the vertical asymptotes always the midpoints?
Yes.
Okay. That's on a
secant and cosecant.
Okay. So it'll
always be there.
Okay.
Right.
It's totally different.
It's totally different on a tangent and cotangent.
Okay, but that's how it works.
But that's how it works on secant and cosecant.
Okay. Thank you.
Thank you for the question.
Okay. So
really, this thing.
Once you get a good handle of your graphs, then we'll have a better
understanding of what the even trig functions are.
Basically, there's only two even trig functions. There's the cosine, and then there's the secant. Those things are reciprocals of each other. Okay. Now let me see if I've got a unit circle somewhere here.
If I have one or not. So.
And that would be super helpful.
If I do that. Let me do this real quick, and I'll come back here.
I just go to my
calculus
1 or calculus 2 class where we can use unit circles quite a bit. Because you all need to see this to help you kind of understand what we mean by even and odd functions.
So just give me a second here.
Be one in here somewhere. Okay, here we go.
Let
me just grab one of these unit circles
somewhere.
Shoot. There we go. That's this thing right here. Okay, here we are. Okay, sorry for the delay. It'll be real helpful
to understand even and odd functions a little better
by observing
the unit circle.
Okay, so I'll zoom on this unit circle a little bit and kind of show you what I'm talking about. So basically, what we mean by an even function
is we mean this.
Like on a
cosine,
it works kind of like this.
I'll just give you an example. So like if we do the cosine
pi over 6, and if we compare that to the cosine of negative pi over 6, this is what happens.
This is why the function is even. So if you look at pi over 6,
the cosine
is the x value.
So the cosine
of pi over 6
is square root of
3 over 2.
Okay, negative pi over 6
just means going clockwise.
So it would give you this value.
Okay. Okay.
So we would get the same value.
And that's what it means for a function to be even.
Is you get this. And it's easy on the unit circle to see that
relationship.
And it won't matter what the angle is.
Notice that if you did
pi over 3,
you have a half.
Negative
pi over 3, you have the same thing.
So that's what even
functions are. If you have an opposite angle and still get the same y value,
then what that's going to
be is that's going to be an even function. Okay.
Everything else is an odd function.
So the sine,
the cosecant, the tangent, and the cotangent, those are all odd functions. So let me just use the sine as kind of a quick example. Okay, so say that you have the sine of pi over 6, and you want to compare that to the sine of negative pi over 6. Okay, what you would find is the sine is the y value. So pi over 6, the sine would be pi over 6. Negative pi over 6 would be this y value. So it's the opposite. So what odd functions are is it kind of works like this. Okay. If you change the angle to an opposite, then you get an opposite answer. Okay, so that's what we mean by an odd function. And if you kind of look at the unit circle, it always has that same structure. You have this angle for a sine, the y value, you go down there, it has an opposite y value. Because on a unit circle, the sine is the y value. Okay, so what you do when you're doing even and odd identity, you don't necessarily have to memorize these identities. But what you have to do is you have to understand what an even and odd function is. Then you can build these identities. So on your even functions, the identity goes like this. If you have the cosine of negative theta, then you'll end up just getting the same thing as the cosine of theta. Okay. And the other even function is the secant. So if you do the secant of negative theta, you end up getting just the value of what the secant is. And that's what I was trying to show you up here is if you do the cosine of a negative angle, you still just get a positive answer. Okay, you get the same answer on that. It could be positive or negative, but you just get the value of the cosine. And the value of a cosine is the x value. So that's how an even identity looks like. And you learn about this idea usually in college algebra classes. Okay, odd goes like this. The odd, we have the sine, we have the cosecant, we have the tangent, and we have the cotangent. These are all odd functions. So it works like this. It's kind of categorize this. So notice when we did the sine. If you look over here at the unit circle I have here, so we got a positive and a negative. So what happens is if you change the angle to an opposite, then the answer becomes negative. So this would be negative sine theta. And so forth. I mean, you can memorize the identities without understanding what they mean. But you'll forget it if you learn it that way. So the way I remember all this stuff is I understand what even and odd functions are and how they work. And once you have those identities, then these problems that I'm going to do on number 18 are actually very easy to do. Sine is an odd function. Since a sine's an odd function, that will give you the opposite of the sine. That's the answer to that problem. Okay, part B, the secant is an even function. So that will give you not the negative, but the same thing. Okay, that's how it goes. So realize if you have an odd function, you're going to have that negative in front of the trig function. Right? So it works like this. C is an even function. A cosine is an even function. So that means if you do cosine of negative theta, you get the same
thing.
That's what that identity
says is the cosine of the opposite angle
will still give you
the same trig value.
It's not an opposite. So that way
that will be 0.4. Cotangent is odd.
So again, if
we do cotangent of negative theta equals this, then this should be the opposite answer.
Okay, so that answer
would be 0.95.
All right, so just to
kind of summarize what I'm doing there, if you have an odd function,
see how you got that?
You got that negative in front of your trig function.
You have an even function. It's the same. There's no negative.
Okay,
Same thing with your
cosine is an even function.
So you get the same answer.
Okay.
All right. Does anybody have
a question about that?
Okay, give me a thumbs up.
Give me a thumbs up if you understand what I'm doing, because I have no clue. Felipe, you in? No? Okay.
Daniel, you okay?
Daniel, you okay?
Okay, and
really, that's a super easy thing to do if you have the identities memorized, but it sure is helpful to really understand the math behind it.
Okay.
Next thing we'll kind of look at here, transitioning is
restricted
range. These are things you have to memorize.
So I mean,
number 19,
and you're going to use
this kind of in the second half of the class
when we get into
a lot more application stuff.
It becomes real helpful to
understand what I mean by restricted range.
And you just have to
memorize these. So they're all a little different. The inverse sine
is
negative pi over 2 to pi over 2.
Okay, the cosine
is 0 to pi. You're given this in radians.
And then the
tangent
is negative pi
over 2 to pi over 2.
Okay, now
what that does is this. Let me use my calculator
to demonstrate
what I mean by this.
Okay, now I'm going to put my
calculator
in degree mode.
Press the mode button.
And it's just easier
for you to see this
degrees than it is radians.
So this is what I'm going to show you.
Okay, so the
idea is
if I do an inverse
sine by doing second sine to open up the inverse sine.
Okay, now
I'm going to put some numbers in and show you what happens. So if I just put like 0.5,
that gives you a
30-degree angle.
I'm going to do it one more time
with something else here. I'm going to do inverse sine of 0.9.
Do that.
I get a 64-degree angle.
Okay, so this is giving you a
quadrant 1 answer.
However,
if you do an inverse sine
of a negative
number, like
negative 0.5. Whoops! I put the wrong thing in.
I put the wrong thing in. Sorry about that.
So if I do inverse sine of negative 0.5. Notice that
I'll get a negative angle.
Okay, if I do inverse
sine of
negative 0.3,
I get a negative angle.
And that's
what your calculator is programmed
to give the
answers to an inverse sine on that range.
So what it really means
when you do an inverse sine,
you're going to get a quadrant 1 answer,
a positive angle,
and you will get a quadrant
4 answer.
Which is a negative
angle. That's how that works.
The tangent
works the same way.
I won't do every example
on that, but if I do inverse tangent of 0.5,
then I'll get
an angle, 26 degrees.
If I do the
inverse tangent of
negative 0.5, I'll get a negative angle.
So it works exactly the way the sine does. And the reason it does is because it's an odd function.
Okay, that right there,
if you look at what I did on the calculator, that shows you that it's an odd function. Okay.
All right. So if you do a cosine,
it'll kind of work like this. If I do
inverse cosine
of 0.5,
that'll give me
an angle that's 60 degrees.
If I do
inverse cosine
negative
0.5 degrees.
Now what it's going to do
is going to give you a quadrant 2 answer. It's going to give you 120. So a cosine, inverse cosine is always going to give you
angle
answers from from 0 to pi.
That's how that gets.
That's how that
so
goes.
It's good to
kind of get a little bit of an understanding of that.
But these are things
you need to just have
on the test.
Okay, on the test,
I just point blank
ask you what those ranges are.
Either know them or you don't know
them. Okay.
Anybody have a question?
Anybody have a question
about that?
About that?
Okay. All right.
Okay. All right. So
the second part
of your test,
you're going to be showing me
that you know how to use your calculator.
Okay. So the second part of the test
is
quite a bit shorter. And you want to the number one thing that you do when you're working with your calculator
is you want to make sure that you know what mode.
Okay.
So
these two problems
right here
are in radians.
These two here are in degrees.
The only time you're in degrees
is if I give you a degree symbol.
If I don't give you
a degree symbol, you're in radians.
So what I would do
on this problem A and C
is I've
got my mode button,
and I would need to
make sure that I'm in the radian mode. Just have that cursor blinking on that, and then you're good to go.
Okay.
Okay.
So here's what you do.
You have to know
that
a secant
of theta is 1 over
the cosine of theta. That's one of the identities we learned.
A cosecant of theta
is 1 over sine theta.
Okay. So the way I put
this in my calculator is I go like this. I go 1 divided by cosine
of 9 pi
over 8.
Okay, like that.
And
I'll put that in, and then I'll just round to however many decimals I said.
So I said
on this round to 2 decimals. So that's negative
1.08.
That's how you put that in.
That's how you put that in. You got to make sure you're in radian mode.
The next one, since it's
cosecant, you have to do 1 over the sine
of 11
pi over 8.
Okay, put that in like that.
That'll give you the answer.
Okay, so that just turned out to be the same answer
because of what the angles were. They don't always turn out to be the same, though, of course.
Okay, so the next one. These are in degree mode.
So
you need to go back
to your mode button,
and then you want to
make sure that you do the degrees.
Get in degree mode.
And then you just type in the correct
symbol.
So
a cotangent
is 1 over tangent. You don't have a cotangent button on your calculator
because a
cotangent is the reciprocal of the tangent.
So what you need
to do on this is just put in 1 over
the tangent of 15.23
degrees.
And then you can round that off.
So that'll be about
3.67. Your answer is a number.
Your answer is not degrees.
Okay, next one.
Just put it in. You have a sign. You have a sign button, so you just put this in.
You'd have negative
285.
And 0.75
like this, and then that will give you the answer. So that is 0.962 would be like that.
So you want to know
how to just do
the six
trig functions on your calculator.
Okay, is everybody okay with that?
Or does anybody need me to
do anything else
with that?
Okay, you're okay.
You're okay. Ricardo, Daniel, Felipe, you guys okay?
Okay. All right. So you have to know
these identities. That's kind of the key thing. How to do a secant, cosecant, and cotangent.
Okay. The next thing
that you want to make sure that you know how to do
is how to do
inverse trig functions.
So what you're doing
on this is asking you for the angle
such that
the cosine is 3.
This one is asking
for the angle beta, so the tangent is negative 2.85.
So whenever I'm asking
for an angle,
this alpha and beta,
those are angles.
And since you're finding
the value of each angle,
that's what tells
you that you're going to use the inverse trig function.
You're working in reverse. So the way you would type
in this first one is you would just say
inverse cosine
of 3.0.
Now the thing
that's kind of critical on this is what I'm asking for in my directions
I want
the answer in degrees. You're going to get an angle, and I would either ask you to give me a degree answer or a radian answer.
So what I need to do
on this is I need to make sure
that I'm in degree
mode.
So I do that.
Okay, so I do that.
Okay, and if I do this,
you're going to get an error on this. Don't freak out if you get an error because sometimes these things are not defined. So if I do inverse cosine of 3,
you're going to get an
error.
That's undefined.
So that's undefined.
Now the reason
that happened on this problem is because of this. Let me go back to my
unit circle,
and I'll show you kind of why this
worked the way it did. So it's good to have an understanding of what's going on with this. Okay, so
here's kind of the idea.
A
cosine is the x value.
Okay, so the
cosine, it turns out that the biggest value is 1. So since on this problem
we had
a 3, that's why it's undefined. The cosine can never be bigger than 1.
That's why we got
the error that we got on that problem.
Okay, next one. You just do this.
You just do this. You just do inverse tangent
of negative
2.85.
Okay, so just put this in. And again, make sure
you're in degree mode.
This one will go
second tangent,
and then negative
2.85,
and that will give
negative 70.67
degrees.
7 degrees. You want to make sure you put the degree symbol on there.
Okay, so that's how
you do that.
All right. The
C and D are trickier for
this is what
I recommend that you do.
You don't have
an inverse cosecant button on your calculator,
but you have identity.
So this is what I recommend that you do.
Use the identity.
You know that the cosecant hopefully is 1 over sine beta.
You want to change that
cosecant to a sine.
Now, what you can do
is you can just cross multiply, or you can even just turn both sides upside down.
You can do the reciprocal
of both sides of an equation.
And if you do that,
you get sine beta
equals 1 over
52.
Okay. So what we will do
on this problem
is we'll enter it in our calculator
this way.
Okay, you got to do the
inverse sine
of the reciprocal of that 52. Right, so if I put that in, inverse sine of 1 over 52. This will give you the angle.
Remember, you're getting an angle when you do this.
So this is
1.10 degrees or just 1.1 degree like that.
So that's how you have to handle it
if it's a cosecant, a cotangent, or a secant.
D,
you do the same thing.
Same idea.
Cotangent alpha
equals negative
1.5.
Change this to
1 over tangent alpha.
And then just do
the reciprocal. And when you do the reciprocal, I'm just turning these things upside down. I'm not doing an identity.
You could also
cross multiply if you want to.
So you just end up
with tangent theta
is equal to the
reciprocal
of this.
Okay,
and then
here's how I put this in my calculator. I just go second tangent,
and then I do
1 over
negative
1.5,
and then just round that up
to 2 decimals. So that will give me
negative
33.69 degrees.
Okay. All right. So using your
calculator, I think out of these problems that I did,
the ones that are the
hardest for students to do are these two.
So you really want to be careful
about how you do an inverse cosecant, inverse cotangent, and inverse secant.
Okay. Does anybody have a question?
Does anybody have a question about that?
Okay. All right. So you'll be able to use your calculator
on those. These problems you can't do unless you have a calculator.
Okay. So let's see.
Next thing we're going to look at. This is one of the earlier things that we learned how to do.
There's two formulas.
And I do give these
formulas on your test.
The area of a sector
is given as 1/2 r squared theta, and you have to make sure theta is in radians. Don't use degrees. Degrees is not a number. Radians is a number. So the only way you're going to get a logical answer on this is to make sure your angle's in radians. Right? The other thing we have is the arc length formula. And the arc length formula, which I will give you, is S equals R times theta. And again, theta has to be in radians. So you're doing this, taking this circle. What you're doing is asking for the area of the sector. And you're looking at this little thing here. It's like a piece of pizza. You're looking at that area of that sector right here. So the first thing you have to do is you have to convert this to radians. And the way we learned how to do that is if you take degrees to radians, you just multiply by pi over 180. Okay, and if you multiply that straight across, you're going to get 45 pi over 180. And you can reduce the fraction if you want to reduce the fraction. You can get by without reducing the fraction. And by the way, your calculator reduces fractions if you don't know that. So if I just put in 45 divided by 180, this will give me the decimal. And the way you can change this back to a fraction is you can press the math button. You press math, and then that option one says convert back to a fraction. So if I press enter again, that just makes that 1/4. So this really reduces to pi over 4. And you can do that on your calculator. If the numbers get really big, you can reduce the fractions that way then. Okay. So to complete this problem, the area is going to be 1/2 the radius. So the radius is 12. And you have to square the radius. Then you multiply that by the angle. So I'm doing 1/2 r squared theta. You do this. That's going to be 1/2 times 144 times pi over 4. And I'm going to just take this straight across. If I take this straight across, I'll get 144 pi over 8. Then you want to go to your calculator. You can do this a little bit differently. You just need to follow the formula precisely, and then just put this in the calculator. So, and what you want to do is use your pi key instead of 3.14. Use this pi key, so you can go second. Then that exponent key, and put it in like that. And then this should give you what that arc length does. Okay. And this one right here, I'm saying round to 2 decimals. So we would say 56. 0.55 if you round that to 2 decimals. And I didn't give you if this was in feet. So if that was 12 feet, then you would need to write the units. So if I didn't give you units, you don't have to do that. Okay. Everybody okay with what I did there? Or do we have any questions on that?
I have a question.
Sure.
I got to turn my
light on too. I can't see
I look spooky.
On my camera. You can see my face.
Okay, go ahead, sir.
So you ran 144 pi over 8 into the calculator and spit out that answer.
Yeah, that's what I did.
Yeah, that's what I did.
You did it in radians.
And it doesn't matter
what mode you're in.
Okay.
If you're working with just arithmetic, it ain't going to matter what mode you're in.
So I just put
exactly like that. 144 pi over 8.
Okay, perfect. Thank you.
Okay. So you don't
really even have to reduce that fraction to pi over 4 because you're using your calculator.
KUN, do you have a question?
I do. So is that answer, do we not say feet squared?
Oh, we do.
Thank you. Okay, I'm not paying attention. Thank you very much. This is an area. So if it's an area, that's in square units. Thank you for pointing that out. Okay. Anybody else have anything on that problem?
Okay. These problems are generally pretty smoothly. I give you the formula.
I give you the formula.
You just
do what the formula tells you to do.
Just make sure that
your
angles and
radians.
Okay. Now we're doing
the arc length. So we use the formula S equals R theta.
So R is
12.
And then theta is
pi over 4.
Okay. Just going to go straight to the calculator.
This would be 12 pi over 4.
And you could
reduce if you want to. That's just pi. So that's the exact answer to the problem.
So what I need to do on that
is just put in 3 pi.
And let's see, that will give
this answer will round up to 2, so that will be 9.42
feet. And this is in feet.
And this is in feet because this is a length of the
arc.
When you're doing an arc length, you are finding
that little piece of
the circle right there.
Okay. All right.
So I think you shouldn't really have any trouble with that kind of problem. You'll see one of each of these on your test.
Just make sure that
angle
is in radians.
Angle is in radians. Because if it isn't,
your answer will make no sense whatsoever.
Okay?
That's what
you have to kind of make sure you understand.
Okay.
Next thing is
the linear and
angular velocity.
So I'll go ahead
and do these.
And then we can kind of
go back and take some questions on some other things.
We may have time
to do that a little bit.
All right. So I
do give you all these formulas. I give you
for linear
velocity.
We have
the formula V equals theta over t.
That's the linear
velocity formula. You take
angle in
radians divided by the time.
Okay, angular
velocity.
Hold on, I did the wrong thing.
It should be this. That should be S over t. I'm sorry.
That's S over
t. That's S of being an arc length.
The angular
velocity
is going to be
theta over
because angular
velocity, what that's doing is it's telling you how many rotations
a circle is going
in a unit of time.
A linear velocity
is saying that arc.
How far does that
arc go in a unit of time? So it's really an arc length over a time.
So it's kind of like
when you're driving a car.
Your tire
is rotating.
If the number of
rotations per minute,
that is an angular
velocity. It's measuring rotation.
But
linear velocity would be something like the edge of your tire. What's its speed? Is it miles per hour or whatever? So it's a different concept.
Okay. The other thing
is we have this formula: V equals R times omega.
And instead of putting the angular velocity
is omega. Let me make sure I've got that
written down correctly.
Linear velocity we use V. Angular velocity we use the Greek letter omega.
So the way that
the linear and angular velocity are related is by this formula.
Okay, so you can
use that on these applications quite a bit.
Okay, so let me
take you through number 4 and what you have to reason out in the problem.
Okay, so
read the problem. It says an object traveling around a circle with a diameter of 8 inches.
And this is the key thing.
It says that it's going at 150 revolutions per minute.
All right. If
I give you revolutions per minute, that means that I'm giving you an angular velocity.
That's what
rotations per minute. RPM. That is what angular velocity is.
So what you do on this
I'm just going to write this down. The angular velocity omega is 150 revolutions per minute.
If you're given
revolutions per unit of time, that is an angular velocity.
However, what I say is I want the answer in radians per second. So you have to do some unit conversions on this. So the first key thing that you want to make sure you know is one revolution. And that would be one lap around the circle. That is 2 pi. That is 2 pi radians. You have to know that. That's a fundamental thing in trivia you have to memorize. One rotation around the circle is 2 pi radians. And I have to do it this way so the revolutions will cancel out. So I've got revolutions in the denominator and then the radians in the numerator. Okay. The next thing is I need to get rid of the minutes. So I need to establish the relationship between minutes and seconds. I want my answer to be radians per second. So you know that there are 60 seconds in 1 minute. So what happens is you're doing these unit conversions, and we call this dimensional analysis is the kind of technique of changing units. You do this like in physics and chemistry classes quite a bit. So now what you can do is you just put this all together. You're ready to go to your calculator. So I'm going to multiply all this straight across. So I have 150 times 2 is 300. So I have 300 pi. The denominator I've got 60. And you can go to your calculator now if you want to. But 300 divided by 60 is 5. So now all we got to do is just do 5 pi on my calculator, and that'll give me the answer of the problem. And let's see, I am saying round this to 1 decimal. So if I do 5 pi, that will give me 15.7 radians per second. Okay, so the key thing on this problem is to understand that I gave you a angular velocity. Okay. All right. You guys have any question about what I did? I think one of the issues that pops up with students on these problems sometimes is not knowing what you're given in the problem. If you're given revolutions per minute, I'm giving you an angular velocity. If I give you miles per hour, I'm giving you a linear. So you got to be really clear on the difference in the units. Okay. All right. Now the next thing is going to say find the linear velocity, and this is when you're going to use this formula over here. You want to use this V equals R omega. Okay, so that's the formula we're going to work with. Is this? And really, what's going to happen on this problem is omega. That was the 15.7 radians per second. Okay, so that's what that was. And then the radius. I didn't give you the radius, I gave you the diameter. So if the diameter is 8 inches, then the radius is always half of the diameter. So the radius would be 8 inches. So you basically got to work this out. And then we got to do some unit conversions on this also. Okay, so we've got the radius is 4 inches, and we have the angular velocity is 15.7 radians per second. All right, so let's do that. Let's see, I'll just do this dimensionally. So I've got 4 inches times 15.7 radians per second. And we're going to have to convert units. So I want the answer to be in miles per hour. All right. So we got to do this. We need to change the seconds to hours. So you know that there are 60 seconds in 1 minute. You can do this in one step if you want to. And then we need to take the minutes to hours. So we know that there are 60 minutes in 1 hour. Okay, so right now we've got the unit of time that we want. Okay. The other thing we have to do on this is we got to take the inches to miles. Okay. So this goes like this. So you'll go like this. There are 12 inches in 1 foot. Okay, so that will kind of take care of your inches. Then we live in the mile high city. So I always tell students, you need to know if you live in Denver, you need to know how many feet are in a mile. Okay, so there are 5,280 feet in 1 mile. And on your test, I usually just put the unit conversions. Give those to you. A lot of times I have international students. I don't expect everybody to have every conversion factor memorized. So I'll give those to you. I'll give something like how many feet are in a mile and how many inches are in a foot, even though you may know that. Right. So anyway, what happens is the feet cross out. Now if you look at this, we've now got miles per hour. And then just to be real careful with what you do on a calculator. I'm going to go straight across and multiply all these numbers in the numerator. Okay, so I'm just going to do 4 times 15.7 and times 60 times 60. And then I'll just go ahead and record what that is. So that is 226,080. Then I'll do the denominator. The denominator is 12 times 5280. Okay, and that will give 63,360. And then we got miles. Per hour like that. And then it's just a matter of dividing those two numbers. So 226, 80. And then divide this by 63,360. So this will give me about 3.6 miles. Okay, and that would be the answer to that. So if you look at these problems, a lot of what we're doing is unit conversion stuff on here. Okay, but if you know the radius, which you were given in this problem, and you know the angular velocity, which we got in part A, then this is the formula that will give you the linear velocity. Okay. Does anybody have a question about what I did? Okay. Study this carefully. This is another thing that tends to be problematic for students. One of the couple of the problem areas in trig on a first exam typically are graphing, and I always find this physics stuff with the angular and linear velocity sometimes is problematic for students. I'll do this last problem here. This one again is an application of linear and angular velocity. All right, so this says the distance from the Earth to the Moon is 228,000 miles. Okay, it says that it takes 31 days for the Moon to complete one revolution around the Earth. So we're going to find the linear velocity of the Moon. Okay, so first of all, we need to know what we're given in this problem. When I see one revolution in 31 days, that's telling me that I have an angular velocity. An angular velocity is always radians per unit of time, or the number of revolutions per unit of time. So this is saying that when you have one revolution, that takes 31 days. Okay. Now, what you want to do on this is you want to convert this to radians per. I'm going to take radians per hour because we are supposed to get our final answer in miles per hour. So what I'm going to go ahead and do is a couple of unit conversions. We know that in one revolution there are 2 pi radians. Okay. We also know that in one day, there are 24 hours. Okay, so what I've got now, by doing that, I'm down to radians per hour. And one thing I want to mention about radians is not a unit. So don't let that bother you. Radians is a placeholder. It's not really a unit of anything. That's the name we give to the real number measure of an angle. So if I go through and do this and just multiply straight across, I'm going to get 2 pi and then whatever 31 times 24 is. And let's say I'll be 744. And then I'm going to go ahead and just do this and maybe round it off to a few decimals or
So we
something
get
like
this.
that. So we get this.
That's going to give
That's
about
going to give about 0.008
4
radians per hour.
Okay, you want to carry out
the decimals a little way on that. So the angular velocity is 0.0084 radians per hour.
Okay, so we got that.
Okay, so we got that.
All right, now what it says,
find the linear velocity of the moon.
Okay, well,
what
we have, remember,
if you know the radius,
and if you know the
angular velocity,
that will be the formula
that we need to use.
Because what's happening
on this problem is you've got
the moon,
and you've got the Earth.
So what we're doing
is this distance
is the radius.
The moon is revolving around the Earth. So the radius is the distance between the moon
and we're simplifying
that. I'm saying I think neglect the radius of the moon and the Earth. Don't worry about that.
So what we'll have
is the radius is equal to 228,000 miles.
Now we're ready to put this problem together.
So
linear velocity
would be the radius
multiplied by the angular velocity, which is 0.0084 radians per hour.
Just
take that on your calculator,
and then that'll give you how fast the moon is going.
So what's kind of interesting
about this, a lot of times to students, and it's interesting to me,
we can figure out
so many things mathematically indirectly.
So you can figure out how
fast the moon is traveling around the Earth mathematically. You don't have to measure it. Literally, you can do it mathematically.
Right. So do this.
We have 228,000.
I got two zeros in there,
and then times
the 0.0084, and then that will give me that the moon is going about 1915.2 miles per hour. Again, don't let the
radian bother you. Radian is not a unit; it's a placeholder. So we are ending up with the miles per hour like that.
Okay, so that's how that
problem can be solved. So really, the big thing
on these type of
problems is the three formulas that I give you. You don't have to memorize the three formulas,
but you do know how
to work with those formulas and work with unit conversions.
Okay. Does anybody have a question
about what I did on that problem?
Okay.
Very good. Now we have
maybe 10 minutes. I got to do
a review with my
calculus class
here tonight. They want me to do a review with that class.
Does anybody have
anything else on here that they would like to
go back and look
at that you're kind of concerned about?
I've got everything else
videotaped if you need to review it.
But we can certainly
go through a couple of more problems.
Anybody have
anything else?
Okay, you in? You're good.
You're good.
Ricardo, you okay?
Okay? Nathaniel?
This might be done,
but can we go over number one? There's nothing dumb about that. I mean, you have to know how to create the unit circle.
So if you guys
want to watch this, number one, you can.
If you want to go ahead and
you can do that too. If you want.
All right, so I can do this.
Real quick, Felipe, and just show you how to
make the unit circle.
Okay.
All right, and if anybody wants to hang out and check this out,
you certainly can. If you don't, then again you can leave. Okay.
All right. So one thing is in
higher math,
like if you're going to take
calculus and things like that,
teachers don't
generally give you unit circles because unit circles
are
actually very easy to make.
They really are.
Once you learn the patterns that exist on this.
The first thing is
these points right here. A unit circle
has a radius of
so
one.
The distance from the center to any point on the circle is 1.
So this point is
this point is 1, 0.
That point is 0, 1.
That point is 0, 1.
-1, 0.
-1, 0.
And 0, negative.
And 0,
That's always a
negative
good place.
That's always a good place to start.
All right. Now,
as far as these other points go, all you got to know how to do is how to count to 3. I'm serious. It's real easy. You'll learn how to do this. And it's also very logical. Your x values get bigger as you go to the right. So in my x, I'm going to go 1, 2, 3, like that.
My y
values get bigger as you go up. So I'm going to go 1, 2,
3, like that.
3, like that.
Okay.
Now, everything you just have to memorize that everything is out of 2. So you divide everything by 2.
The other thing you
got to do is you got to do the square root of the numerators.
Okay, so just getting the
1, 2, 3 is real simple to do. That's how you get your points. That's one of the reasons why
we don't like to
have students always looking at a unit circle because it's so easy to create.
So this one
you just write this point as a half, square root of 3 over 2,
and then this one is square root of
2 over 2, square root of 2 over 2,
and then this one
again you have square root of 3 over 2, and then
that's all you got to do.
That's all you got to do to get those points.
And then what happens over here
is these points reflect.
If you reflect that over the
y-axis,
all that's going to do
is it's going to change the x value.
So you'd have negative
-1/2,
negative root 2 over 2,
and
negative root 3 over 2.
The y values would stay the same.
Okay, so I'm just going to
put a check mark.
Take the time to write that out.
But they're the same.
Things also reflect
over the y-axis. So if you reflect over the y-axis, then it's the y values that become opposite. So you go straight down, that'll be negative root 3 over 2.
Straight down,
that'll be negative root 2 over 2.
Straight down,
this will be
negative 1/2.
And again,
the
x values stay the same.
Okay. And then over here,
it's just basically a reflection. It would be kind of the same way.
Okay. Do you guys understand?
Do you guys understand how I came up with that? Okay.
All right.
Okay.
So that's how you can come up with that.
The other thing that I can do real quick, I have time to do this, but I got students trying to get in here.
What I like to do
is
count by 45
degree
A lot of times
students don't understand
that you can create
these angles.
You don't have to memorize them.
You don't have to memorize them. All you got to memorize
is
pi over 4 is 45 degrees.
So watch how I do this.
I'm just going to go 0 pi over 4.
Pi over 4. Counting by 45
2
pi over 4.
2 pi over 4.
Which reduces
to pi over 2.
3 pi over 4.
3 pi over 4.
4 pi over 4.
4 pi over 4.
Which reduces to pi.
5 pi over 4. 5 pi over 4.
6 pi over 4.
6 pi over 4.
3 pi over 2.
3 pi over 2.
And then this would go 7 pi
like that. 4 like
that. That's all you got to do.
That's all you got to do. You don't have to memorize all those angles. You can count them out.
And then the last thing is,
you have to know is pi over 6
is equal to
30 degrees.
So you can do this.
That's pi over 6
and then you just do the same thing.
You just do the same thing.
You're counting out
30 degree increments.
So if you just keep counting
those out,
this was going to go like this.
You have pi over 6.
This one would be 2
pi over 6.
This would be 3 pi over 6. 4 pi over 6.
4 pi over 6.
5 pi over 6.
5 pi over 6.
6 pi over 6.
6 pi over 6.
7 pi over 6.
7 pi over 6.
8 pi over 6.
8 pi over 6.
9 pi over 6.
9 pi over 6.
10 pi over 6.
10 pi over 6. Now, I'm not reducing fractions, but you do want to reduce fractions.
So that's it.
You can count by pi over 4.
And you can count by pi
And you can count by pi over 6.
Okay, and that's something.
Before you take the test, just print yourself out a blank unit circle and just see how quickly you can get that put together.
Okay.
All right.
All right. Well, guys, I got to get ready for my next class.
Thanks for coming in.
Thanks for coming in.
And I'll
if you need to see me or anything, or
contact me.
Contact me.
Or you take the test,
just let me know.
There's a chance that
if nobody wants to take their test Friday, I might have some availability where you could come on, and if you needed some help getting ready for your test, you could do that.
Okay. All right.
Okay.
So work hard,
study hard, and
let me know when you're going to take the test.
Okay.
Thank you.
You're welcome.
You're welcome.
So quick question.
Yeah.
So did you by chance post that first video of the review?